Hey, Intro Engineering Design folks. This is lecture 2 about material properties. This is part 2, investigating other properties. I have a feeling that I have made a bellwork about this before. I've actually uploaded any lectures for y'all, so let me double check that I run this lecture. So when you're thinking about making a product, the size you make it, the shape, the volume, the weight, can all impact what it looks like, the visual, functional, and structural characteristics, and the cost of materials, and the cost to process and manufacture it. But also what type of materials you pick can also impact all the same things. You've got physical properties that include things you can measure, like the size of something, the volume, the weight, the mass, density, conductivity, elasticity, and so on and so forth. And then there's mechanical properties. These properties specifically apply to how your material responds to an externally applied force. So a force is anything that's a push or a pull, and that includes how strong something is, the strength of it, the yield strength specifically, which is like if I put mass up here on this, how much mass, how much weight, how much force can it withstand before the material itself starts to bend and deform completely and not go back to its original shape. Tensile strength has to do with things that are in tension. I don't know if y'all can see my projector is hanging from like a column of, I have no idea if you can see this. My projector up there, you may or may not see that. I can't tab out and check. But it's hanging from like a column, a metal column. That's under tension. If I've got weight at the bottom of it, that's pulling down, and it's held on at the top, so it's got tension. And so that's tensile strength. Things like ropes. Will the rope snap or not? Hardness, that's to do with like, can I scratch part of it off? Stiffness is, does it bend or flex at all? And ductility has to do with, can I pull it and draw it out into a wire, or like metals, a lot of the time if I stretch them out, they'll make a wire. Other materials, if you start pulling on them and they start to stretch, then they break. So you think about, does this type of material, does it deform permanently when you pull on it, when you push on it, compress it, when you break it? Like, how hard do you have to hit it to break it? Can it flex and pop back to its old shape? Things like that. That's mechanical properties. Your electrical properties are how your material responds in the presence of an electric field. So that includes conductivity. Does it conduct electricity? And resistivity. Does it resist the flow of electricity? So basically you're trying to figure out, is it a conductor or an insulator? And how much of a conductor? How well does it conduct? How well does it resist? How well does it insulate? Your thermal properties is how your material responds to externally applied heat and just rapid change in temperature, things like that. So heat capacity, that's how fast it heats or cools. Thermal conductivity, does it transfer the heat through it or not? Thermal expansion, that's when you warm something up, it gets larger, like the material expands a little bit. This is particularly true of gases. Most engineers don't have to work much with the gaseous state. Usually you're working with solids. But some of these solids, like metals, a lot of the time will expand and contract when you heat and cool them. And you talk about melting points and boiling points. In physics, what that is, like if I have, let's say I've got ice in a cup, just ice. As I heat up, as I add energy to that ice, it's going to increase to the melting point, which is also the freezing point, because if you're going lower, that's going to freeze, which is 32 degrees Fahrenheit or 0 degrees Celsius. At that point, I'm going to keep adding energy to my ice, and as it melts, it's not going to increase in heat. It's just going to turn into water. Like all the energy I put in is going to turn that ice to water, and it's going to sort of mix in. It's going to be ice and water until it's all water. Once it's all liquid, then the energy I put in is going to heat up the liquid again. So the liquid's going to get warmer and warmer. And then at boiling point, which is 212 Fahrenheit or 100 degrees Celsius, at that point, the energy I put in is not going to heat that water anymore. It's going to turn it into steam. And as it's bubbling up into steam, the water's not going to heat, nothing heats up anymore. If I had it sort of in a enclosed area, if I was heating it up, it would all stay the same temperature until, well, if it was enclosed, it'd be pressurized. It'd be complicated. But basically, the energy I put in is now changing it to steam, not heating it up any farther. So steam can get really hot. That's why it's dangerous. That's a tangent. So think about, does this material expand as it heats up? Is it a thermal conductor or insulator? If I have it on the outside of like a spaceship, is it going to keep the heat in, or is it going to let the cold through, or let the heat out, I guess? Can it tolerate a rapid change of temperature? If I put a glass dish in the oven and heat it up very, very hot, and then I go and I'm like, I'm going to put it under water and rinse it out, and I put very cold water in it, is that going to shatter? Will it soften during processing? You might want it to soften, or you might not. If I'm running metal through a machine that's supposed to stamp it out or bend it into a certain shape, and as I'm running it through the machinery, it heats up, It might soften, it might deform, it might not hold whatever shape I try to make it. Your optical properties, these are fun. If I had finished engineering school back in nerd school, this is what I would have wanted to do. My optical stuff, a lot of fun. It's how does your material respond to externally applied light sources? So optics has to do with, glasses, lenses, mirrors, telescopes, cameras, lasers, holograms, all sorts of fun things, tricks like that. But for our purposes, that includes like what color light does it reflect? Does it reflect purples? Does it reflect blues? Does it reflect red light? What kind of wavelength of light does it reflect? How much light does it absorb? How much energy does it absorb? If I have a dark roof, it's going to absorb a lot of light energy and keep the house warmer than if I have a lighter roof color. Transmittance, how much light does it let through? Is it completely transparent? Is it just translucent? You can kind of see through it if it's enough light. Or is it opaque, completely hard to see through? Reflectivity, does it bounce light off of it at all? Fluorescence, does it glow? And refraction, which has to do with does it bend light? And I say a good example of this is if you ever see like the Pink Floyd Dark Side of the Moon album cover, they've got a prism on it. And the white light's coming in here. Inside the prism, it bends out the different wavelengths of light, so they spread out from each other. And on the other side, it's got the rainbow of all the colors of light coming out. And that's what refraction is. It bends light. And that's how lenses work. That's how, anything that changes light coming into your eye to make you see better works. So anyways, another tangent. Does it absorb or reflect light? Is it clear or not? Is it translucent, opaque, whatever? That's optical properties. Magnetic properties are how does it respond to magnetic fields? Is it attracted or repelled by magnets? If it's a dipole, it's both. Is it neither attracted nor repelled? Things are not magnetic sometimes. Is it magnetic? Like, does it have a strong magnetic grip on something? There's a question in the bell work that you may already have seen because I've delayed getting this one online. Sorry. Where my question, the word magnet is in all four of the options. And one of them is basically, hey, if you ever put like a magnet on the fridge and try to hold like a picture or something up with it, and it'll hold one picture up, but then let's say I put like a paper underneath it or 2-3 papers underneath it, I start to put a bunch of paper in there, that magnet might not hold those things anymore because there's not enough magnetic force between the two surfaces and things are going to fall off your fridge or it might slide down the fridge. That's just the way magnets are. Some of them are stronger than others. Chemical properties. So this quantifies how reactive a material is to externally applied chemical agents. Reactive means like this material, this will change. The composition will change somehow. Includes things like, especially how it might degrade over time. That's what really applies to us for engineers. How reactive is it? Is it going to react with water and like sodium, I believe? If you put straight up sodium in water, it's a very violent reaction. Is it combustible? Does it set on fire? What kind of surface energy does it have? What's the pH? Its acidity and basicness. Is it corrosive or not? Does it resist corrosion? So think about how quickly does it corrode or rust? Rust is corrosion. Does it fall apart? Are you making a handrail for something and the material will corrode with the oils from people's skin just touching it constantly and it's going to get warped and ruddy and gross and disgusting? How quickly does it corrode? Does it react with acids like vinegar? Like if I'm making a container to cook in and I'm going to want to put vinegar in this container, I don't want this to react with vinegar. I mean, you cook with vinegars, you cook with a lot of acidic things, and you cook with a lot of basic things. You have the whole pH spectrum. You don't want it to react with the different pHs very much. So you want something that's very kind of neutral in that regard. It doesn't react either way very much. That's chemical properties. I don't like this slide. I've skipped it in class. If you want to read it, you can. We talk about the power of observation. If we're trying to figure out what something is made of, we can look at it. A lot of the time, they'll give us clues as to what it's made of. A lot of the time, if you have experience with materials, you kind of already have a good idea. Like if I were to look at my computer mouse, this one, it looks like plastic to me. There's a clear spot in the bottom that probably is more plastic. There might be some glass in the lens for the optical parts there, but it's probably mostly made of plastic. There's probably metal in the wiring because I know it's got to go through there. But looking at it, I mean, you look at it, what color is it? What's the luster? That's how shiny is it? A lot of the time, metals are very, very lustrous. They can at least be polished to look that way. Ceramics too, I think. Glass 10. So how transparent is it? Can I see through it? If I can see through it, it's probably not a metal. If I can't see through it, well, there's a lot of things it could be. But that gives you some ideas just by looking at it. what it might be. You can also feel things. Weight, you can sort of feel how heavy something is. If you have two objects that are about the same size and one of them weighs considerably more, you can infer that one's more dense, the heavier one. How much heat is transferred? If I touch this item to something that's hot, do I feel the heat coming through it? And that's important, like for pots and pans. Let's say I've got a pot on the stove. I'm not going to touch the pot material. That part's supposed to heat up. If I hold onto a handle over here, though, I don't want that to be super duper hot. So does heat transfer through material or not? That can tell you what it is. If it doesn't transfer at all, it's probably not metallic, because usually metal will transfer heat. How stiff is it? Does it bend or flex? How hard is it? Can I scratch part of it off? That's the touch sense. And then you can listen to it too. Polymers, like plastics, tend to thud. And I did an example where I knocked on this bottle. Of course, it sounds different depending on where you hit it and how, but I'm about to hit it and squirt it on myself. So wood tends to make a knock. And ceramics, and I brought this out because I had a ceramic dish. Ceramics tend to make a sharp sound. I don't know if you're going to be able to hear it. It has a sharp noise. Let's see if I can hit it with something that's not going to break it. I got a pencil under my computer holding it up. A lot of the time you'll have, I was going to say something and I forgot. So I guess if I remember it, I'll let you all know. What I've tried to do, I was thinking about making another section of the slides about quantifiable parameters. What else is there besides density? What are some parameters we talk about as engineers? And when I got to this stage, I realized I was just copying out of a table, and I don't need to do that to y'all. So the one you have doesn't have quantifiable parameters in it. Let me see if I have it open somewhere, though. Do I download properties and materials? There we are. This thing right here. I'm going to upload that here. And what this is, just to tell you what it is, I can make it any larger, not really. So this table that I'm going to put up here has a bunch of common parameters that measure the material properties that really interest engineers usually. You don't have to worry about how to calculate this yet. I mean, that's something you'll get into later on. We're going to work with density. That's the only one I kind of want you to be able to calculate. But it's more important right now that you understand kind of why this matters to engineers. So look through this document. It's going to go with the activity that's for the 9th and 10th. You've got 3 columns. One is the material parameter, and that's in your SI units. And there's an explanation column and an importance column. Your density, for example, it'll tell you also the variable usually used in physics and engineering and math equations using this quantity. It looks like a lowercase p. It's actually a lowercase rho. It's a Greek letter. It looks kind of like a P, but it's tilted and it doesn't have the top part that sticks up a little bit. And then it tells you the units. So you can do kilograms per meters cubed. That's just a unit of mass per unit of volume. You've also seen grams per centimeter cube, or grams per cubic centimeter, or grams per milliliter. As long as you're consistent with your units, you'll be fine. So it'll tell you what it is. That's the measure of mass per volume, and it'll tell you why it's important. Why does it matter? Density, well, that's a material engineers use to estimate the weight of a product. If I'm designing something and I know about the size it's going to be, if I think about something like, I'm going to make it out of steel, that's pretty dense. It's going to be pretty heavy. If I need it to be something that someone's lifting a lot, I don't want it to be really dense. I want to find a way to lower the density. Especially if you have weight constraints, especially if you want to, let's say you want to ship something, but it's going to cost a lot of money to ship it. And so you want to reduce the weight so that you don't have to pay as much in shipping. That's one way you might have to use the density to think about how heavy this stuff's going to be. You also use it to identify unknown materials. We're going to hopefully, I have packages arriving today. I don't know what's in all of them. But hopefully we're going to have this stuff. If I can weigh something, get the mass of something, and I can also then find the volume of that same thing, I can calculate its density. And we have a whole bunch of information about common material densities out there in the world. If I don't know what kind of metal something is, I could just look at a table and say, okay, I've got the mass, I've got the volume of this particular sample, I'm going to calculate its density. It's about whatever. And then I look at my table of metals and I'm like, okay, this one's pretty close. It's probably made of nickel or something. So that's what we can do to also just figure out what stuff is made of. The next few are about strength and if it breaks or bends or deforms. So yield strength, that's to do with pushing a force against something. Like if I have an I-beam and I put weight on top of it, I've got it supporting part of a building. How much can I put on top of that I-beam before that I-beam starts to bend and permanently change shape? This is also available on the PLTW site, and all these little things are linked. And I can probably write this up for you too if you don't know how to get on PLTW's website. The tensile strength, that's kind of similar to the yield strength, except now we're talking about something that's being under tension, like the column up there, or like if it's a rope or something that's hanging down and it's getting pulled down. What amount of tension can it be under before it snaps or deforms in some capacity? Your shear modulus. Shearing is about twisting. Like if I am turning a bolt and I'm turning it and like the material suddenly starts to actually bend instead of it biting into something it's supposed to. So that's about shear. How flexible is it? The modulus of elasticity has to do with like if I squish it down, does it bounce back? Like is it elastic? How much can I compress it to have it come back to its original shape? Ductility is, can I stretch it out, make it skinny? If I were to stretch, like if you pull on a piece of chewing gum, that stretches pretty far. If I were to pull on a piece of, chicken, it doesn't stretch very far. You got toughness. These both have to do with braking. If I figure out the impact energy, like how hard do I have to hit it to break it, higher the better, because it doesn't break. This one resists the propagation of a crack. Propagation of a crack, that's like if you ever see your car get hit by a rock, your car windshield hit by a rock and there's a little crack, a lot of the time it'll stay that way. They've found a way to make glass in such a way that it doesn't just shatter into a billion pieces when you get hit by one little rock. Sometimes you'll see, like if you get a decent enough hit with a rock, you'll see that crack actually goes off to the side and bends up or something like that, and it like moves away from where it was hit. And that's to do with how much tension the glass itself is under. It's really interesting. But if you don't want a crack to propagate if you can avoid it, right? You don't want a little tiny crack here to shatter the whole thing. Hardness, that's like, does it resist deformation on the surface level? Like, can I scratch at it? Can I knock into it without smushing it in a little bit or peeling parts of it off? Electrical conductivity. So conductivity and resistance are very important because electricity, it's a fickle thing. If I have too much electricity running through something that's not meant to have that much electricity go through it, it can cause serious problems. If I overload, like if I plug the wrong voltage into my computer, it could fry all the circuits, If you are working on your computer parts, you take apart your computer, your program, your controller, like your PS3 controller, PS5 controller, what are we on now, 5? If you take your controller apart and you've got little microchips and you get static on your finger and you accidentally zap it, you could melt a little part of your circuit you didn't need to melt. So that's why you take every opportunity to reduce the static when you have when you're working on electronics. So if I have conductivity, I want this energy to flow through it. That's good. If I want if I know that I'm going to plug it into the wall and I don't need that much electricity, I'm going to need a bunch of stuff resisting it so that when I get to my little delicate components, it doesn't just fry the whole thing. Melting points. You need to know at what temperature will this product fail completely because it melts. Like you have your cookware. It says rated to 400 degrees Fahrenheit, rated to 450, rated to 500. Your oven mitts, they're rated usually to a certain temperature too. Things like that. Your little trivets that you put your hot food on. Hey, it won't melt until you get it this hot. That's good to know. Thermal conductivity. If you need to move heat from one place to another, you want good thermal conductivity. If you want it to be more of an insulator, like if you've got, your house, your windows, you don't necessarily want the heat of the sun to come through those windows and heat the house in the summertime. Specific heat is kind of how fast something heats or cools. That's how fast it changes temperature. How much heat can it absorb before its temperature rises by 1 degree, usually Kelvin or Celsius. They're the same size, degrees are. That is really cool, and I wish I had a calorimeter because we could do something like that, but it's okay. You'll do that in physics, hopefully. High values are favored in products that will store heat and keep the heat. All right, so your coefficient of thermal expansion, that's when it heats up, how much does that change? How much does the shape change because it's heated up? If you ever have like a metal pan in the oven, sometimes when you put it in there and you're baking cookies or something, and after a little while you hear this pop because the metal's warping a little bit because it's getting hot. Then you go to take it out and you set it down, it kind of warps back to normal again at some point, pops back to normal. Something you might notice is if you have a plastic water bottle, and it's been in the fridge all day, and you drink some of it and it's cold, and you put the lid back on and you got a space that's full of air up top. If you let it sit out for a while, that air especially, but also the water is going to expand a little bit as it gets warmer. And so when you go to open it, it just had a little fizz sound it made when I did that. And sometimes if you drink some and then you've had it out all day and it's hot and you put it in the fridge or freezer, as the air and the water sort of contract a bit more, it'll actually pop in the sides of your bottle in certain places. So you've seen this happen, I bet, once or twice. Anyways, that is up here. That is for your next event, and I think this is already like super long. 20 minutes. Guys, have a good one. I'll see you soon.